My name's Amar. I work at Parity, started 2 months ago, and it's been really good. It's great to work on open source work and get paid for it. So I'm going to be talking about building DAOs with Substrate today, focusing less on code and more on mechanism design, but there is a decent amount of code. So I'm going to start out by motivating DAOs, specifically fund coordination DAOs. After that, I'm going to give an overview of Moloch Dow, which is the project that I ported the logic of Moloch Dow to Substrate. So that's the code I'll be walking through. And then I'll be talking about why Substrate is an especially useful framework for building DAOs, and then a few ideas of other crypto-economic mechanisms that could be built on Substrate. Okay. So this is a quote from Jorge Izquierdo of Aragon, and I guess I'll read the quote because it's a good quote. So for the first time in history, we will be able to experiment with different human governance models from the comfort of our chairs. In previous eras, trying out new governance models could end up very badly for society, even with wars or human catastrophes. So blockchains provide us with a very rich playground for testing and experimenting with different organizational structures. And for this reason, I believe this technology is uniquely suited to tackle coordination problems, specifically tragedy of the commons and free rider, etc. So the classic example is fund coordination, and it's the specific use case that I'll be focusing on in this talk. So despite a relative abundance of resources, we consistently struggle to coordinate efficient and meaningful allocation to those in need. So within open source, we see this problem close to us. Most maintainers are forced to self-fund their own open source work and receive no external funding, and this isn't acceptable. At the same time, it represents an enormous use case for coordination mechanisms that could first and foremost benefit deserving developers, but this could also have enormous second-order effects that would accelerate the pace of progress in our domain. So the context is fund coordination DAOs. So Moloch Dow is a fund coordination DAO on Ethereum that strives to tackle the tragedy of the commons problem facing Ethereum infrastructure development. Most token holders, and this problem can essentially be summarized by the fact that most token holders don't want to share their profits, but they benefit significantly from protocol development and infrastructure progress. So this situation sort of epitomizes the tragedy of the commons and free rider problem that we see in open source. I think Moloch Dow is a great experiment. I hope it's successful. And I tried to build a similar thing on Substrate. So it's called Sunshine DAO, and this is the GitHub repo. That's the logo. It's kind of like Mimblewimble, but it's different. So yeah, I tried to demonstrate Substrate good best practices. I joined about 2 months ago, so I'm still learning. I might actually update it because I learned a lot from preparing for the UTX workshop tomorrow, which I'm doing with Nicole. So how does Moloch Dow work? What is the basic setup? So first we'll go over the logic, and then I'll go through the code. But shares are essentially a governance abstraction in Moloch Dow, and they're useful for signaling with respect to voting on new proposals, and these proposals have to do with issuing new shares, but they're also useful as an exit mechanism. So I'll sort of explain how proposals work over the next few slides, but these are the two things that you can do with shares. So to apply for shares, applicants actually require sponsorship from existing members. Some good drawing. Applicants must also offer capital. So this is what the token tribute, they call it a token tribute in Moloch Dow, and I use the same term. The token tribute essentially says how much capital they'll devote to the DAO, and then they also specify the number of shares that they're requesting. So you might wonder, like, how is this a grant-making DAO? It sounds like a social club for ETH holders, and it is kind of that as well. But approved grants can be invoked via burning the shares. That's how you exit, and that's how you get the collateralized stake, the proportion of collateralized stake that you have ownership of. So it's not super obvious, but members can actually, so the way a grant would work is members can approve a proposal that doesn't lock up additional capital, so the token tribute is really low, and then maybe instead the proposal provides some proof of ecosystem contribution. And then once the proposal would be approved, the applicant would burn their shares to access a proportional share of the capital locked up by the DAO. And the capital withdrawal would represent the applicant's grant. And that condition at the bottom, no pending proposals can be supported by the member, it's very important. I'm going to sort of go over why it's important in the next few slides. So actually first I'm going to go over scaffolding, and then I'll touch on those two, lock-in and instant withdrawal. So scaffolding events are a good place to start when you're trying to visualize the state transitions within a Substrate module. So proposed is an event, and after a proposal is submitted, this event is emitted, and the fields are proposal hash, the token tribute is the balance, the sponsoring member is the first account ID, and the applicant is the second account ID. For aborted, it's the proposal hash, the token, it's the same ones as proposed. And then for voted, it's the proposal hash, the vote, so yes or no, the yes vote count, and the no vote count. The remove stale is just the proposal hash, and processed is the leaving member's account ID, the number of shares that they had that were burned, and the amount that they withdrew. So there is a lot in our runtime storage. So these are the config values, and I'll probably use, well, I'm going to use two of the maps for a later example, but they sort of give an indication of the fact that we need voting windows, which we'll talk about. Okay, so these are the runtime functions, and these are, obviously, they're not full of any logic. I just wanted to sort of present them to you guys. So the propose allows a member to sponsor an application to the DAO. All of these, I should mention, all of these functions can only be invoked by members of the DAO, and that's a choice that Moloch Dow made that I sort of inherited. So at the top of every one of them, there's like a let who equals ensure signed origin, and then you check membership based on that address. So the vote function allows members to signal approval or dissent against a given proposal with a share-weighted vote. Process allows members to execute proposals that have been passed. Ragequit allows the DAO members to burn their shares, withdraw proportionate capital, and leave the DAO. So yeah, a quick reminder that within these functions, all the checks are done at the top before the storage changes. We'll see how that's done. Okay, so these are the two key features I mentioned earlier, lock-in and instant withdrawals. And after many lessons of DAO, through DAO experimentation, we've learned that instant withdrawals are important, but lock-in's also important, so that when you vote on a proposal, you're forced to essentially commit to your decision that it's good for the DAO. So once if a member votes for a proposal, they have to wait until it passes a grace window to leave the DAO, and members that voted against the proposal can leave the DAO during that grace window. Okay, so this is just a graphic of showing how lock-in works. So if they voted for proposal B and it's in the grace period, they cannot leave. But this guy could leave because he voted no on the given proposal. So like, if you think about this for a little bit, you might see like a problem arise, and the problem is that this guy can't leave if there's any proposals in the yes queue because of lock-in. So in practice, implementing lock-in and instant withdrawal is somewhat limiting. It places a tacit limit on proposal throughput, or at least how we can interact with proposals. So after a proposal is submitted to the proposal queue, the voting period is initiated, and members can signal support for or against the proposal until some defined threshold. But once the voting period ends, the proposal is scheduled for execution. So if approved, the grace period begins, during which the dissenting members leave the DAO. But the basic problem here is that you can't leave if you voted yes on any proposal. So this is actually a condition that we sort of have to uphold if we're going to ensure the safety of lock-in, because otherwise we don't have lock-in, and lock-in is important. Okay. So before we discuss our implementation, just some basic, like discussing how the objects are set up. So this is what's fed to the proposal function, and or the fields of this struct are fed to the proposal function, and then this struct is instantiated, and then it's encoded and a hash is taken, and that hash is used as a unique identifier in many of the maps in the decal storage to keep track of the proposal. But the hash is also kept natively in this struct as base hash, and this is the struct for each proposal, which contains all of the fields. Okay. So in our decal storage, there are many maps, but the two maps we're going to focus on for the purposes of our example, which is implementing that condition such that you can't withdraw unless you have no pending proposals. We're just going to use proposals for, which is it tracks all the proposals voted for by a given DAO member. So that's a map from the account ID of the DAO member to a vector of hashes. And then the voters for tracks all the voters that supported a given proposal. So that proposals for is going to be really useful for the condition that we're checking because it tells us if there are any pending proposals that have been supported by a given member. Okay. All right, so this is actually the last method. Let me see. Yeah, this is the last method in the DAO RS file, and I'm not going to really go into depth on what the code says because it is some relatively complicated Rust, but it essentially removes the proposal hash from all the vectors in proposals for upon the call to this function. So if you trust me that I placed remove proposal in the correct places of the DAO RS file, then we're correctly removing proposals from this proposals for map. And then this is sort of how it would work. The Ragequit function would work is it would check this proposals for map, and if it's empty, that means that you could exit. And there's some other storage changes that I didn't include, but that's sort of the important check for upholding this variant, which is that you can't leave without making sure that you don't have any pending proposals. Okay. So yeah, one thing I wanted to mention though, and there is something of a mistake here, is what if the member that wants to leave sponsored a proposal? So they didn't vote for the proposal, but they sponsored it. And in that case, they would still be able to leave according to this implementation, but fixing that problem isn't that hard. We just add a check in the, we just add one line in the propose function where we essentially just add the proposal that was sponsored to this proposals for map. And that way it sort of accounts for the possibility of a member sponsoring a proposal. Okay. So we still have a few problems. There's of course the problem of preventing proposal spam, and then also how do we incentivize actions by members? So these two actions would be sponsoring proposals, and then how do we incentivize processing, which occurs during the grace period, so sort of finalizing the proposals. And so one thing we could do is, the obvious answer for number one in terms of incentivizing or in terms of essentially preventing proposal spam would be bonding each proposal in terms of both the applicant and the sponsors. And then for the second one, for incentivizing membership actions, we can use those bonds in order to pay both the member that sponsored the proposal as well as the processor under different scenarios. So I'm going to go through that really quick. So for bonding, we import the currency trait, and this is sort of what it looks like. You guys can look at the code after too. But this is how we bond proposals. So we use the reserve function on currency, and this is the same way that I've seen it done in staking, maybe council as well. But you reserve the proposal bond, and then we're reserving token tribute for applicant. The way we would implement a proposal bond for the applicant is we just have this ensure statement where we make sure that the token tribute is above the proposal fee, which is something set in the config. Yeah. Okay, and then we unreserve with this. And the basic pattern is you reserve to bond, you unreserve to unbond, and if you're transferring the bond to someone else, then you unreserve and then transfer. So let's see, yeah, this is unreserve and then transfer if the proposal fails. So that's how that would look. But I want to get to something else first. So there's a lot of hidden complexity. It's very difficult to manage all of these different conditional paths that we sort of encounter when we build DAOs. And I didn't answer these bottom 3 questions, but they're worth asking, and I haven't really addressed them with my implementation. The bottom question especially is very interesting. Phil Dian has good research on that if you're interested. But one thing I wanted to mention, so Autonomous is this DAO, and Autonomous uses an auction pricing algorithm, token bonding curves, issuance that corresponds to collateralization of another crypto asset, and then on top of that, they use conviction voting according to the secondary token ownership. So there's a lot going on here. And the point I sort of want to make is that even if something like this achieves some theoretically optimal equilibrium, mechanism simplicity is important, and it determines both the diversity of users as well as the rate of adoption. So accessibility is the degree to which an environment is usable by as many people as possible. And I think that it's a criteria worth establishing when we're building DAOs. So rather than alleviating friction with users, adding token abstractions, even reputation for an internal metric inevitably ostracizes certain classes of users and makes your DAO unusable. So when you build your DAO, you need to consider the target demographic rather than blindly optimizing for Pareto efficiency. And above all else, sort of what I want to say is that we do not want to create another system where those most familiar with the rules thrive while others most struggle with basic interaction. Okay, and this is a Stephen Pinker quote. So as we progress, new problems are going to continue to arise that we're going to need to address, and I expect these problems to primarily correspond to accessibility. Okay, yeah, there's some other stuff. But yeah, so if we're gonna target accessibility, then we're going to have to continue to iterate with this assumption, and Substrate essentially provides us with upgradability that we haven't seen before because we compile Rust to WASM, and that facilitates on-chain upgrades. And then also something to note is that deployment in the context of Polkadot fosters shared security without the expensive spillover costs. So that allows for experimentation in parallel, which I think is really important. And I didn't really get to this slide, but the Hawthorne Effect basically says that sequential testing means that we will stop prematurely. We'll stop when we think that we have a solution instead of continuing to experiment with our parameterizations. Okay. Yeah, that's it. So, thanks.